We are trying to find out what this term, how this term behaves, and when we understand this term better, we will be in a position to understand whether indeed, where I had written the overall expression, the second order term which we had looked at, which we have invested so much effort behind looking into, right, that p g prime squared plus q g squared, whether that term indeed predominates. It might be positive, but is it positive enough to supersede or predominate the effect of this? Now this term also varies with respect to this alpha squared, but within here are there alpha dependencies, and I put it to you, and that's exactly going to be my next step here. Yeah. So, but then how do you know what happens then? I mean, that would assume that you understand what gamma is, and that would assume that you would also be able to then push forth with all those claims and those variational equations and all the effort that you put in to establish, yeah, that you could pull it out and find it and write it down as a perfect square and so on and so forth, right. See, this gamma is something whose existence we know of, it is not a constructive proof here. Just like that C tilde, existence of that C tilde was guaranteed, but I am nowhere using the mechanism to find that C tilde anywhere in my proof. I am just happy with the fact that there exists some C tilde at which you will be able to, between A and B, there is some intermediate value at which if you evaluate the second derivative, you will get an exact accurate expression, not an approximate one that the Taylor series throws up when you evaluate it only at A throughout. All the derivatives and the function value of f is evaluated at A, then you cannot truncate that series without any error at any point, yeah, always you will be accruing some error. But if you at a strategic point, at the second derivative point for instance, if you evaluate it at that C tilde, you will be making no error. So now we have a handle on this term in the sense that we know what it looks like, but do we really? Of course, there is this explicit appearance of alpha squared here, and this tells us nothing more than what we already knew. What about the term inside here? Is there an alpha dependency? That is going to be the key crucial observation here. What is the difference after all based on? Some gamma you have chosen. What is the choice of gamma based on? The alpha that you had chosen to begin with. So if you make alpha small, wouldn't the gamma also become smaller, because gamma is contained between 0 and alpha, isn't it? So if you make alpha small enough, this term, what happens to it? Becomes smaller and smaller. So as you make alpha smaller, this actually reduces. I am saying this in a rather loose manner. If you want to write down the expression of this explicitly, you can do that. You can call this, so you can actually carry out integration by parts on this term, yeah. You can carry out integration by parts on this particular term, and then you will have the appearance like O alpha squared, and you can guess what the integration by parts will lead to, right. You'll basically have to get rid of the, oh I haven't, G prime, yeah, sorry. So you'll have to basically get rid of this cross term like we did. Only thing is now you will have alpha squared integration A to B, maybe a P tilde G prime squared plus Q tilde G squared dx. And now all these P tilde and Q tilde, they are actually differences between the tilde terms in terms of the Lagrangian and its partials and the actual L. So as you make alpha small, this term gets smaller and smaller, right. So therein is the alpha dependency. So already there is a quadratic dependency here. In addition, this term also converges to 0 as you make alpha small. So this in fact goes to 0 definitely faster. Okay. What is it that we are trying to say here now through all of this? I am not writing explicitly what this P tilde and Q tilde is, yeah. You can just You can do that. P tilde is very easy to see. It's just going to be, just half of this. Q tilde will involve this minus ddx of this. Straightforward, just the same trick again, right? But what is the main crucial observation here? That this goes to 0. So let's look at, for example, O alpha squared by alpha squared. This is equal to integration a to b p tilde g prime squared plus q tilde g squared dx. Something else is even more interesting here. If you divide both sides by the square of the one norm of g, remember what the one norm was? It was the maximum value attained by g plus the maximum value attained by g prime within that interval. Yes? So if you divide that, then of course p tilde gets multiplied by a quantity that is smaller than 1, as does q tilde. So therefore, if you were to now do the following, O alpha squared by alpha squared and the one norm of g squared, this is definitely less than or equal to a to b p tilde. So the max of this p tilde plus max of this q tilde. Is this part clear? So in fact, it actually doesn't matter how g behaves. It's actually a uniform kind of a result, right? See, you couldn't have done this with the zero norm of g. If you divide by the zero norm of g, the zero norm only considers the magnitude of the function, not its derivative. But here, because when you divide it by the one norm on both sides, this one gets divided by the one norm squared. That's a quantity less than 1. This quantity also gets divided by the one norm squared. That's also a quantity less than 1. Yeah. So you can actually look at this and say that, okay, that's pretty good, because there is a uniformity in this convergence kind of a thing. Yeah. So the key essence of this entire derivation is the fact that this p tilde and this q tilde get smaller and smaller. So of course the maximum value that they can attain in the interval between a and b is also small, provided you make alpha small enough. So that means there exists alpha small enough so that what? What happens? So that this O alpha squared is smaller than or equal to, you can just pull it out there, isn't it? Just cross multiply on both sides by this denominator, really. Yeah. So that O alpha squared is less than or equal to integration between a to b p tilde, okay, let's still call it the max, plus max q tilde. So alpha squared. Now without loss of generality, you can take the g to have a norm of one norm of unity. Doesn't really matter, no? So then you can also get rid of this term here, and this is all you are left with then. Yeah. So indeed this seems reasonable to expect that this term gets predominated by the second variation, but we still need to establish it. Still a few steps are remaining. Let's complete the formality. Are there any doubts about all these expressions that we have written so far? Are you convinced that indeed if you make alpha small enough, p tilde and q tilde both get closer and closer to 0? because depending on the alpha you choose, the gamma gets even smaller, and depending on the difference between 0 and gamma, the difference between L and L tilde and their partials, of course the relevant partials, they come closer and closer. So those terms all vanish in the limiting sense. So there will always be some, you give me some number, so that you want every one of those terms to be smaller than that number, and I will be able to find that. How I will constructively find it is another problem, because that will invoke the mean value theorem and explicit solution of certain equations, but there exists, and that itself is good enough for me. Okay, let us look at our original term that we had, a to b p g prime squared plus q g squared dx. We already assumed that p is positive, right? Initially we started with the loose necessary condition that p is semi-definite, positive semi-definite, but then while going through Legendre's equation and Legendre's path, we said that okay, p is positive and the whole squared was also positive unless g was identically equal to 0, right. So we already convinced ourselves that p is positive. So choose delta such that p minus delta, of course do not forget p depends on x, just for the sake of brevity I have omitted all these arguments here, yeah, all of them are functions of x, please be mindful, these are not constants, okay. So this delta is of course a constant, yeah. So if you have a positive number, no matter how small it is, there will always exist some number in between that positive number and 0, let delta be such a number, yeah. So then what happens, p minus delta g prime squared plus q g squared dx, sorry, a to b. Now suppose this is a term which you want to ensure is positive, what do you have to do? You have to now replace p with p minus delta in your variational equation. Remember that equation we started with in today's lecture, Jacobi's equation. So find out v, and because of the continuity of the solutions with respect to parameter, if the original equation in terms of p and q, that original Jacobi's equation in terms of p and q has a solution, we will argue that by the continuity of the parameter solution with respect to the parameters in the equation, when you make a small little perturbation such as delta here, you will still find another v, or you call it v bar or whatever, v hat, such that it will also satisfy that Jacobi's equation and not cross 0. So if the original does not have a conjugate point, then this modified one will also not have a conjugate point, and in that case we know that this is greater than 0. It's a whole square, right? So we've already assumed that to begin with the original p and q pair yielded a solution to the Jacobi equation that did not give rise to a conjugate point. So therefore the modified Jacobi equation with p minus delta and q will also not give rise to a conjugate point due to the continuity of the solution with respect to parameter. The other day we talked about this continuity of the solution with respect to initial condition, now we are talking about the continuity of the solution with respect to a parameter, yeah. Of course there is a lot to investigate there, I am just saying it very loosely and you are probably believing me, but things have to be investigated whether actually the solutions are continuous. Sometimes in certain wicked kind of differential equations, subtle variations or small variations in parameters or initial conditions can lead to widely varying solutions, but the Jacobi equation is not one of them, thankfully. You have to believe me on this, I am not going to prove this, yeah. So therefore this one is also going to give rise to a positive quantity just because the original PQ pair gave rise to a positive quantity, but this then implies that the original fellow with P g prime squared plus Q g squared dx was greater than delta times a to b g prime squared dx, yeah, pretty straightforward up until this point. This is okay, clear, right? The argument behind all of this, anyone can write these lines, yeah, you can copy them from a book, but you should understand the reasoning we are providing behind each of these steps. Okay, let's just look at something else here. G squared. Wonder how we might write this G squared as. We could write it as one squared. That's the reason why I'm writing it in this fashion. Or rather, let's say, okay, not now. 1 dot G prime dx a to x It's true, right? I mean, you can just, yeah, that's correct. Now, does this remind you of something? Something that you've seen in Euclidean spaces? A dot product, perhaps? What is an inner product in the space of functions? Like we argued a few days back when we spoke about these Fourier series and these different cosines and sines and orthogonality thereof. If you have a function f and a function g, and if you integrate fg dx over an interval, that's the inner product, right? Yeah. So I put it to you that this is actually the inner product of 1 and g prime, or at least has the similar appearance, except that it's integrated over a to x and not a to b. Yeah, but okay, let's see. If we in general allow this to be till x, okay, you might, if you're a Puritan, you might just replace this with gamma over here and put this as x over here. Really, it wouldn't matter. But now, what is the one important, the most important inequality you have learned when you learned about inner products? The Cauchy-Schwarz inequality, right? So what does the Cauchy-Schwarz inequality tell us here? The dot product or the inner product is less than or equal to the product of the individual norms. So if you have squared this, then this would be less than or equal to what exactly? Sorry? Yeah, so you have to take 1 squared. Yeah, so you have to take a to x 1 squared dx. That's the norm of the first fellow, and the norm of the second fellow is okay. If you're bothered with this thing here, yeah, just replace it with a dummy. This is g prime squared, isn't it? G prime squared dx. So that's less than or equal to, what is this? This is just x minus a, right? X minus a times the integration a to x g prime squared dx. But now because g prime squared is a positive integrand for sure, so if you integrate over a longer interval, it only grows. So I can just write this as x minus a integration a to b g prime squared dx, right? Just an application of Cauchy-Schwarz inequality. And let me now use the central part of the board. So if I now consider integration g squared dx a to b, that's less than or equal to integration x minus a to b. Look, this part now becomes a constant, no? Doesn't meddle with the integration of x minus a at all, right? So this is dx times integration a to b g prime squared dx. And what do you see here? Really, this is something very familiar to us, exactly something we've been discussing, exactly something that allowed us to say that p cannot vanish or p cannot be negative at any point in the interval, we cannot say the same about q, because the derivative tends to predominate. That's exactly what's being shown here, right? You see that? Because now what we have is the integration of g squared dx is less than or equal to, what is this? B minus a whole squared by 2 integration a to b g prime squared dx. So you can always scale up the square of the derivative suitably, and this will always trump it. You cannot do that with the other way around, can you? Right? So the derivative always tends to trump this. This is a more explicit characterization of the result which we showed with that weird sinusoid function that we cooked up a couple of modules back, if you remember, right? So this is exactly the same thing that's telling you. But what's the benefit of all of this? Now, remember that term that we had, which was p tilde g prime squared plus q tilde g squared dx integration a to b, yeah, that was what this term was all about, isn't it? Right? Recall that this was true. We just showed it a while back. I in fact erased it from here. Right? What can you now say about this? This is less than or equal to what is it? If you want to pull out g prime squared outside, what do you have to do? Bound this by its maximum value, bound this fellow by its maximum value, but there's also this factor, the scaling factor between the relation between g squared integral and g prime squared integral is this b minus a whole squared by 2, right? So this fellow is actually going to be smaller than or equal to the max of p plus the max of q tilde times b minus a whole squared by 2 . Of course, I am not writing that x belongs to a to b, yeah, you understand what the max is taken over from the context. We will just clutter the expression all the more, times what? Times the integral between a to b of g prime squared dx, isn't it? Yeah. Just look at this expression here. Because through your choice of alpha, you can make p tilde and q tilde as small as you wish to, like we argued a while back. Choose your alpha so small that both p tilde's max value and q tilde times b minus a whole squared by 2's max value are bounded below delta by 2. What happens then? On the one hand, you then have that O alpha squared by alpha squared is smaller than delta, smaller than or equal to delta, whereas the second variation is greater than delta, of course times the same integral. So by a comparison, you can clearly say that the second variation will always trump the O alpha squared by alpha squared, which is what we needed. The fact that the second variation was positive was established yesterday, subject to the satisfaction of the two conditions that L y prime is positive and there is no conjugate point. The positivity was not in question even before we started the discussions today. The only thing that was questionable was, what about those other higher order pesky terms? What if they manage to trump the second variation? But now we see that That will not be the case. So indeed, the condition that L y prime is greater than 0 and that there is no conjugate point when you solve for this Jacobi's equation, V does not vanish over the interval, is actually sufficient second order condition to ensure that the candidate that you have shortlisted through your solution of Euler-Lagrange equation, the extremal that is indeed going to minimize your cost. However, the dampener to your spirits after all of this work is, this is a lot of work, not just the proof I mean. You don't have to do this proof again, right, once you've attended this course, as long as you remember the result. But remember what you have to do, you have to evaluate L y prime, you have to also solve Jacobi's equation, you have to figure out whether that fellow has a 0 crossing in the interval a to b, and once all of this checks out, then you say, oh, okay, it's done. On the other hand, it may very well be the case that instead of doing the second order check through your solution of Euler-Lagrange equation, you've already shortlisted a reasonable number of candidates. Among those reasonable candidates, now you evaluate the cost function with each one of them substituted in the cost function or cost functional, and you know which is doing best. That's it, right? So computationally speaking, these results were indeed, of course, they're very interesting from the analysis perspective, I'll put it anyway, but these results were way more important back in the day when we didn't have computational facilities. But today when we can compute things just using the first order condition, first order necessary condition through Euler-Lagrange equation and shortlisting the extremals might be a much more efficient way to go about things than to actually check the second order sufficient conditions, okay. But the point that we have established and throughout this lecture today, what we have established is that not only is it positive, but it does trump, that second variation does trump the other higher order terms, and in order to establish that, we have had to go through all this mechanism and all the calculus lessons you might have learned during your sophomore years in engineering, right. So that's where we will put a stop to this discussion on hardcore calculus of variations, and that's also going to be the syllabus for your first quiz. This is where we will stop. From the next lecture onwards, we shall depart slightly from considering these C1 functions. We will see that sometimes piecewise C1 functions, which are also known as broken extremals, you might have to accommodate those possibilities, and I will give you a simple physical example. When the length of the catenary, when the length of the cable is very long, so long in fact that it will actually sag and touch the ground, then the curve that is generated by such a cable is not going to be a C1 function, because at the 2 points at which it begins to touch the ground and takes off from the ground, those are going to be what we call as corner points. So in fact that function is piecewise C1. So there are 3 segments of it. One is the descending part of the cable, the other is the part of the cable that lies flat on the ground, and the other is the ascending part of the cable at the other end as you go from left to right, yeah. So it's piecewise C1, but at those points where it breaks, or so called broken extremals, which we call as corner points, they are not, the derivatives exist, the left side derivative and the right side derivative exist, but they are not equal, so they don't blend in very nicely. It's piecewise C1, it's C0, but only piecewise C1, okay. So how to study those broken extremals? Will our original Euler-Lagrange equation still hold? Well, they will hold for the entirety of the curve, but some special conditions need to be also found out vis-a-vis these corner points. Some other additional conditions have to be met at these corner points, and an even bigger question is, how do you even know where these corner points are? So it turns out that those additional conditions will give us the locations of these corner points, and we will admit a wider class of functions now than the ones we have considered through classical calculus of variations thus far. So that's all what we'll begin to study from the next lecture onwards. Thanks.